Hello, class, and welcome back to math. We're starting a new course. It's called Analytic Geometry. In this class, we will take a look at geometric situations and we will prove things or show things about them using algebra, midpoint, distance, slope, all kinds of things. But it's heavily relies on Algebra 2 skills. So it's a great review in Algebra 2. We're going to start though with some review. And today we're going to be looking at the coordinate plane, and we're going to be looking at just the distance formula because it's used through the entire course. Now, don't think it's just the basics. A lot of times we'll review the basics and then expand upon it and go into it in a lot further detail than you've done so in Algebra 1 and Algebra 2. So let's get started with analytic geometry. Here we go. So today we are taking a look at section 1-1 and 1-2. Now 1-1 is just a review of the Cartesian coordinate system. Section 2 is going to be the distance formula. Okay, so let me tell you something about this book. We're using the Analytic Geometry book by Riddle, and in this book, some sections are just a little short review and have no assignment over it. That's section 1-1. Some sections then follow up with more on the next lesson, and then they go on and cover an assignment at the end of it. So 1-1 is just a quick review. So let's review the coordinate system. This is the system you've been graphing on since 5th grade. Recall there are divided into 4 sections. When you make a Cartesian coordinate, it divides the plane into 4 different regions, and those regions are called quadrants. Now, the quadrants, the way they're named is that this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4, and generally they're named with Roman numerals. In these quadrants then, this is the quadrant, both the X and the Y coordinate, all of the coordinates are X's and Y's, this being the X axis, this being the Y. So everything in this quadrant, both the X coordinate and the Y coordinate are positive. In this one, the X coordinate's negative, but the Y is positive. We're negative on the X, positive on the Y. In quadrant 3, both the X and the Y are negative. In quadrant 4, the X is positive and the Y is negative. Don't forget the name of that little special point there. That's the origin, or the ordered pair 0, 0. Okay, that's just a quick review on the coordinate plane. Now that we've got that, let's move on to the distance formula. With the distance formula, it's really unique the way this was founded. The history of this is great. I encourage you to look it up one time about how Descartes was watching supposedly a fly on the ceiling and how he could describe where that fly was exactly. So it's kind of a unique story. Let's say this is point 1. This book loves subscripts, so get used to little subscripts. Point 1, and let's say this over here is point 2. Whereas we're used to in geometry calling it A and B, this book uses subscripts, P1 and P2 for subscripts. So this would be the first X, and that about there is the first Y, or excuse me, the second Y. And here is let's try that again, X1 and X2. Here we have Y1, and about right there is Y2. So when we go to name this point would be X1, Y1, and this point would be X2, Y2. Why that bothers me. I like arrows on there. Okay, so here we go. Let's talk about how this formula is derived. If I want to find the distance from P1 to P2, what we take a look at is basically Pythagorean theorem. The length of this segment right here would be x2 minus x1. And the length of this side of the right triangle would be y2 minus y1. So when you take a look at, let me just call this C for now. When you take a look at how these three relate, Pythagorean theorem should pop into your head. By the way, Pythagoras did not come up with Pythagorean theorem first, but he just got credit for it. Just a little more history for you. So here we go. This side squared plus this side squared equals this side squared, or C squared is equal to x2 minus x1 squared plus y2 minus y1 squared. Now, let's solve for C. We just want C. We don't want C squared, so we would have to take the square root of both sides. And when we do that, we would end up getting that C, which is actually the distance from P1 to P2, which your book does this distance notation. When you see in your book, they say find P1, P2 with a bar on it. In geometry, usually you're taught that no bar on it, that means distance. But in this book, a little bar on the top, that means what's the distance, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Ooh, barely fit that in. Okay. So we've got this now. This is the big formula for distance. Let me just outline it in red. Oh, I tried. That pen doesn't work. Let's try another. Here we go. Let's outline that in red. There is the distance between points. You will do that so many times this year that you will laugh if someone says, what's the distance formula? You're like, we use that all the time. Okay, so I want to remind you that this distance is always positive. You should never give a negative number in this class for distance. Now, there will be some times later on we talk about vectors where distance will have a negative or positive sign to show direction. But for this unit, distance is always positive. Just like if you're saying, what's the distance is it to Lufkin? Is it 20 miles there and negative 20 back? No, it's 20 miles there and 20 miles back. So distance is always positive. Well, let's do some examples now, just to refresh yourself. Let's do some examples. So here we go with the examples. First one, find P1, P2, or P sub 1, P sub 2, the distance if P1 is 1, 4, and P2 is negative 3, 2.
Your PIN followed by pound.
All right, so how do we find the distance? So P1,
PIN followed by pound.
so P1, P2 is equal to, let's see, above these, I'm going to say, let me call that X1 and that Y1. We're going to call this the second X and the second Y. And let's see what we can do with that. So the square root of X2 minus X1, that would be negative 3 minus 1 squared plus 2 minus 4. So we just substitute into our formula. And then we'll get what? That's a negative 4. So that's going to be 16 plus 2 squared, negative 2 squared is going to be positive 4. Remember, both of these numbers should always be positive because you're squaring them. So careful putting those in the calculator with parentheses. So that's a square root of 20. Now this book is going to most likely have you simplify. So 20 is 4 times 5. So it looks like the distance is 2 square root of 5. And we'll go ahead and simplify for this class because a lot of times we're using simplified versions of it. There are some times where you're comparing these distances where you might need to take a look at an estimate. So if we grabbed our calculator and did an estimate for that, that's about 4.5 units long, the distance from the 2 points. Okay, so far so good. It's very important in this class that we label things. What did we find? We found P1, not just scratch work all over the place. We found P1 to P2. So labeling is going to be very important in this course. If you don't label something on a quiz or test, you might lose a point on it. Okay, so let's take a look at this. Let's bump it up a little bit. That's just the basic thing that you did in geometry and in Algebra 1. Let's take a look at another example. Find x if P1 is x0, P2 is 2, 5, and P1, P2 with a bar on it, which means the distance between P1 and P2 is 5 times the square root of 2. All right, look at that problem. Well, that looks fun. Let's see if we can just set up the distance formula. The distance formula, we already have the distance. 5 times the square root of 2 is equal to, now let's set up that distance. Okay, let's see, here's x1. Well, let's try it again. There's x1, y1, and there's x2, y2. So here we go with our formula. 2 minus x. I'm going to go the other way though, because it doesn't matter. X minus 2. I just like it that way. X minus 2 squared plus 0 minus 5 squared. We've got it all set up. Now we just have to solve for x in that equation. This is where your algebra skills come in. So let's see what we have there. We have 5 square root of 2 is equal to, let's do some multiplying out here. Let's see. I'll just leave this one alone. But we'll go ahead and multiply that out. That's negative 5 squared is 25. Now to get rid of the radical, we're going to have to square both sides. I'm going to have to take this and square it and take all of that and square it. So we're going to square both sides. In that case, we need to square the 5. That's 25. Square the square root of 2. That's just 2. Square root of 2 times square root of 2 is 2. And that's equal to square the square root. Those kind of undo each other. And so you just get x minus 2 squared plus 25. Now at this point, let's see, I'm going to go ahead and write 50 on this. At this point, we need to multiply things out. So this is x minus 2 times x minus 2. So first outer inner last or double distributive, whichever the way you learned it. X times x is x squared. Minus 2x outside. Inside minus 2x. And last, negative times a negative is a positive 4. And then we have the plus 25. Let's see if we can move everything on one side. So I'm going to put that minus 50 over there and just get a 0. So now we have 0 is equal to x squared. Let's combine some like terms. Negative 4x. And now let's see, we have 4, 25, and negative 50. That's 29 minus 50. Let's see, what is that? Negative 21? Okay. It's a quadratic equation. We have a lot of choices here. First, we're going to try factoring. If factoring doesn't work, we'll try quadratic formula. Completing the square, we could have done that with the plus, but if we'll try it, let's start with factoring. If factoring doesn't work, we'll move to quadratic formula. So are there two numbers that multiply to give you negative 21 and add up to negative 4? I think there are. I think there are. Let's see. That's going to be 7 and 3 give you 21. I want -7 and +3. Let's check it. X squared minus 7x plus 3x is -4x. -7 times 3 is -21. That'll do it. So here, if two things multiply to give you 0, the zero product property says that this one has to equal 0, or x plus 3 has to equal 0. So x is equal to 7, or x is equal to -3. Okay, we've got our solutions. Now, part of me wants to know, why in the world did we come up with two solutions? Why did we get two solutions? I want you to look at this on a graph, because here's where the analytic geometry comes in. Let's analyze, why did we get two solutions? So we had the point x0, which means there's some point on this axis, because it doesn't go up or down at all. So x0 is somewhere on the x-axis. And the other point was, let's see, what was it? 2, -2, 5? 2, 1, 2, 3, 4, 5. So here was point 2, and basically we were asked, where is point 1 on this axis? On this axis, where is point 1 such that its distance is 5 square root of 2. Do you see why we can go either way here? Okay, we could go 5 square root of 2 and find a point here, or 5 square root of 2 and find a point here. In fact, we did. This one would be -3. We got -3 as a solution, and this one over here is 7. So that's why there are two solutions to that. We were saying, find a point x0. What's the x value on the x-axis? What value of x makes the distance from point 2 exactly 5 square root of 2? And that's why we had two solutions. That's the analyzing part. I just think this part of this class is great. Let's try some more. Let's see what else we can do with this. Let's bump it up some more. How about this one? Determine if 1,7, the point 0,3, and the point -2, -5, determine if those are collinear. Oh, I wish you were here in person with me. I would say to you, what is collinear? Do you remember collinear? All the way back to geometry. Look at that word that's in the middle of it. Line. Collinear means they fall on the same line. So we're trying to decide if they fall on the same line. So basically, we're going to be given 3 points. And let's say we're given these 3. If we're given these 3, let me call these A, B, and C. This book doesn't do that, but every once in a while, we just need to label something. If A, B, and C are on a line, and I found the distance AB and the distance BC, AB plus BC should exactly equal, this distance plus that distance should exactly equal the distance from A to C. Okay? Now, if they're not on the same line, then the distance from AB plus the distance to BC will not equal the distance from AC. It'll be larger. So we need to find out, basically we're asking ourselves, is the distance from AB plus the distance from BC, is it equal to the distance from A to C? Now I say that, I may need to check these points and see if they're in the right order, but let's try them. I think I need to call this one C and this one B for this problem to work. So here, let's see. I think that the ones furthest apart are those, because if you look at 1, 7, 0, 3, and -2, 5, I think we're going to have to do it this way. Anyway, we'll just look at the distances, find all 3 distances, and look for the longest one. So let's start with the distance AB. Distance from A to B. I called this one B. So that distance is the square root of, let's see, -2 minus 1 plus -5 minus 7. That's what? That's 3 squared is 9. Yeah, that's 9. And this is 12 squares, 144. So it looks like that's the square root of 153. Okay, let's try the distance. That's AB. Let's try BC. And it really doesn't matter which one you call A, B, or C. BC, these two. That is -2 minus 0 squared plus -5 minus 3 squared. So let's see. That's going to be 2 squared, which is 4. And that's going to be 8 squared, which is 64. Looks like that's the square root of 68. Okay, now we need to find AC. AC. Let's see, -2 minus 1, square root of -2 minus 1. Whoops, I've already found that. No, I already did that one. Let's try again. It needs to be A and C are right here. 0 minus 1. Sorry about that. Pay attention here. 0 minus 1 squared and 3 minus 7 squared. Okay, so let's see. That's 1. And that is 4 squared is 16. So it looks like the square root of 17. Okay, so this is obviously the large one here. I don't have those in the right order. Let's see if I can write them. The larger one is AB. So we're wondering if AB is equal to BC plus AC. That's the longest one. Do these two add up to that one? So one thing you can do is try your calculator. All right, grab your calculator and try it and see. The other thing you can do is simplify these radicals. If you simplify these radicals, let's see, we've got the square root of 17 plus the square root of 68, and we're wondering if that's equal to the square root of 153. Well, let's see, I see that 17 in there. I think this just so happens to be 4 times 17. So this is the square root of 17 plus, that's going to be 2 square roots of 17. And guess what this is? This just happens to be 9 times 17. So if I simplify these radicals, I get that that is 3 square root of 17. And look at that. 1 square root of 17 plus 2 square roots of 17 equals 3 square roots of 17. It's true. So we can write out conclusion. The 3 points are collinear. Now, in this class, I want to point out a couple things. Labeling is so very important. If you just do scratch work all over the place and I can't figure out what's what, you're going to lose some points. So what I need you to do is label points that you were given. I did A, B, and C. I should have just left it A, B, and C. But label some points. Find the distances. Look at that. Labeled, labeled, labeled. Show your work, and then your conclusion. This is not the answer to the problem. All of this is the answer to the problem. So make sure you show me that work. Let's do one last example, or just talk about this last example. I don't know that we'll work it all the way through, but let's do one last example. Show that these points, let's see, 1, 2, 4, 7, -6, 13, and -9, 8 are vertices of a rectangle. Okay, so show in this class, that word show in this class is huge. That's where the analyzing comes in, analytic geometry. We're supposed to show that those 4 points form a rectangle. There is no such thing as proof by graph, like draw it on a graph and say, oh, look, it's a rectangle, done. There's no such thing as that. You have to show supporting work, but you can start off with taking a look at graphing it. Let's start off with taking a look at graphing this thing. Ooh, that one goes all the way up to 13. Okay, so we go up to 13. Okay, I'm looking at all our points here. -9, -1, 2, 3, 4, 5, 6, 7, 8, 9. If you want it to look like a rectangle, do your spacing pretty equal there. See, the highest we go up to is 4 over here. The highest we go up to is 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, let's graph these now. 1, 2. Let's give them some names. Let's call them A, B, C, and D. All right. So we've got A is at 1, 2. We've got that's our A. We've got B is at 4, 7. That's B. We've got C is at -6, 13. That's C. And D is at -9, +8. Maybe. Okay, you can see. Oh my goodness, I can't draw a straight line. You can definitely not tell from my graph whether that's a rectangle or not. Cannot tell. Let's talk about how do we know if something is a rectangle? Can I just find this distance, BC and AD, and show that BC is equal to AD? And that, so if I show this is equal to that, and AB is equal to DC, would that be enough to show that that's a rectangle? I hope you're thinking, no, it's not. That means it's a parallelogram. Oh, we're going to have to remember some geometry that's in this class. That would show it's a parallelogram. It could look like this. And these sides are equal, no sides are equal. So that's not enough. Now, here's the key right here. We need to show that those two are the same, because in a rectangle, the diagonals are equal. The diagonals are equal in a rectangle. So we also need to find AC equal to BD. So what you would have to do here is find 1, 2, 3, 4 distances. You would need to find AB and CD and show those are the same. You would need to find BC. Let's see, BC and AD and show those are the same. That would get opposite sides are equal. Then you need to show the diagonals. AC is equal to BD. You can see in this class why labeling is so important, okay? A lot of times in the problem, they won't label it. So when you write down the problem, I want you to label it so that you can refer to them when you find all your distances. Now, we're not going to finish that, but I just wanted to talk about it. When you're finished, you would need to write a reason, something like because, and I'm not sure if this is actually, because ... the points form a rectangle, or because ... the points do not. So you need to work this out, and you would show all that. You would show, once again, all your work, a graph, all your work, and then a sentence to tell me what your conclusion was. This class is very, very important. In that sometimes there's a lot of work to be shown for one problem, but very importantly, you have to show all your work. Okay, show and label all your work. Very important. That wasn't necessarily true in trig, but it is in this class. Okay, I want to talk about some other things. How would I show that something was a rhombus? just to make sure you got it. In a rhombus, all I need to show is that all four sides are the same. In a parallelogram, if they say, is this a parallelogram, then all you would need to do is show that opposite sides are equal in distance. This distance and that distance are the same, and those distances are the same. Here you have four distances all the same. And finally, in a square, how do you show that something is a square? Is it enough to just show that all the sides are equal? No, that means it's a rhombus. Okay, you have to show all the sides are equal. Then you have to show that the diagonals are also equal. Okay, so I just wanted to go over that with you. Now then, your assignment in this book is assignment, it's on in section 1.2, we're going to do 1 through 27, the odd. Today is just working with distance formula. There's just a lot of different applications for it. But have fun with these, and if you have any questions, feel free to shoot me an email or give me a call. Have a great day. Bye-bye.